Okay, how was the homework assignment?
It was okay.
It was okay, kind of difficult, not too difficult, too tedious. Go ahead.
It was pretty, it was steep at first, but then once you understood it, it was pretty.
That's the whole idea. Okay, so that's good. That means it's working for you, because you basically just you have to. There's a little bit of learning curve. You have to learn the tools, to also learn the approach itself. But once you get it, it's just kind of tedious. You can make silly mistakes to kind of break the program, but once you understand how it works, you kind of look for those things like, okay, did I pop something off the stack? Did I balance the stack pointer? Because those are the little things that can break your program.
Yeah, the tracing helps.
The tracing helps. Knowing what to trace and what to look for and how to interpret the trace helps a lot too. But that's studying. So you guys have been studying. If you have been doing the homework assignment the right way, you have been studying the whole time. Okay. So what we'll do today is going to kind of finish up this topic by working on a few more examples. And I can give you some example of what I asked in previous exams. But since I'm actually still in the process of changing how I want to teach this class, so there will be some changes between the version that I had here and your version. So we can take a quick look. So there will be questions like this, where I will give you the assembly. I will give you the C code, and you have to give me the assembly code, okay, using the toy processor. The instruction set has changed a little bit. Well, not changed, but we have extended the instruction set. So the instruction set that you will be seeing will be the extended version. The opcodes document will still be the up-to-date description of everything that you will be tested on. Okay? So in question number 1, you just have to write the assembly code either in mnemonics or in the pseudo-C notation in order to implement this particular program. In question number 2, it is a decompiling process. So you have to read this code and then go backwards and figure out what is the subroutine, what the subroutine is doing, and the logic of the subroutine. Okay? But if you have been writing your homework assignment should help you prepare for this. So we can go through this too today. And then we have question number 3. Use microcode slices to implement a new instruction return to perform all the operations related to returning from a call at the end of a subroutine. That's actually pretty easy because we already have the individual pieces. Okay, what are the individual pieces to return from at the end of a subroutine? You guys should know that by now. Okay, wait. Before we jump, there's something we have to do first, right? The stack pointer is register D. What do we do with register D? Before we do something with D, go ahead. Do a load first. Okay, very good. We do a load first because the stack pointer will be pointing to the return address at the end of a subroutine. So the first thing is a load instruction, LD, and then you have to waste one of the registers, B or C or D. You don't want to use A because A typically has the return value. So you have a load instruction, and then what is the next one? An increment, because we want to deallocate that byte on the stack. And then the last one is a JMP instruction. So if you want to roll all 3 into one single opcode, what do? 3 slices. You just borrow the first slice from LD, the second slice from increment, the third slice from JMP. That's it. Just a concatenation of those 3 slices would do it. Okay? So I'm hoping by now you guys know what I'm expecting when I ask you about the start location in microcode ROM. No?
Can you explain that?
Okay, let's go ahead and let's check out this particular one and figure out what we can do with this. Okay. Use microcode slices to implement a new instruction return to perform all the operations related to returning from a call at the end of a subroutine. The opcode of this new opcode or this new instruction is 0x02. So if 02 is the opcode, where do you think is the start location of the first slice corresponding to this entire family of opcodes? 0 to 0 in ROM. Why do we have that the last 0?
That is it.
Because we have 4 bits of 0 when we copy the instruction register into the microcode pointer. We have 4 zeros.
Do you have that on the share drive?
No? Oh, not yet. Let me make a copy of this. Make a copy to shared. And I think we can put it into fx answers. So we'll put it over here and click select. There we go. You should be able to see it now. Let me know if you cannot.
It's under, what is it?
It's under,
FX answers.
yeah, it's under fx answers. Can you see it?
Yeah.
Okay, cool. Excellent. Okay, so I can actually put the answer here. So the start location in ROM is going to be 0x020. Okay, that's the base. But you have to read the rest of this instruction. Assume register 0 is used as a stack pointer. This instruction may use all registers except for register A because it is typically used for return value, so you don't want to overwrite register A. Assume this instruction can use the other 2 registers B or C, B and C in any way, and this is a single opcode. So as a single opcode, 020 is all you need. Because we're not parameterizing it using registers. But within the instruction, you can choose, which register to overwrite, for the return address. Is that okay? All right. So how do we get this done? Now it doesn't say anything about, you have to use the question marks and stuff like that. Oh, before I forget.
You found my wallet.
I texted you on that day.
Did you?
Yeah, on last Thursday, the moment, the person handed me the wallet, I texted you.
I didn't get any.
Using the Moodle
Oh.
texting thing.
Messenger.
Messenger.
I see.
Okay.
Thank you very much.
Oh, you're welcome.
You were right.
Yep.
So sorry that it's going a little kind of backtracking here, but you said earlier there was the 3 pieces of the 3 slices that we're supposed to combine. Could you go over what that was to make return?
Right. So those 3 slices, using our current instruction set, is going to be a LD A. Okay, not A, but use B or C. The first one is going to be an LD instruction because this one will copy the return address to register B. Because the return address is assumed to be pointed to by the stack pointer at this point of the subroutine. Is that okay? Because the return instruction is used as the last instruction or the last opcode in a subroutine, so this is when we're about to get back to the caller. So the return address is expected to be pointed to by the stack pointer at this point. But once we use it, you have to remember to increment the stack pointer. Basically, we are deallocating the return address from the stack. And then the last instruction is a JMPB instruction. So what you need to do is to look up what is the slices for, or the first slice of the LD instruction, the one slice for the INC, the increment instruction, and the one slice for JMP instruction. Kind of make sure that you use the registers correctly when you're selecting the registers, and you're done. Now, because it is in the previous test already, this particular question will not be in your test, but something similar, may be in your test.
So
Yep.
we would just take like the first slice of each one of those and then
Right.
put them in here.
Yep.
And then what if you asked, or we thought one with 2 slices would be relevant? Would we then have 4 slices instead of 3? So a command that used 2 slices?
Right. So then you will only have 2 slices instead of 3. Not sure whether I answered the question.
Yeah, that's all right. I'll ask you.
Okay. So that means something that you might want to consider is to use this as a resource. So go to the current opcodes folder these programs may be helpful to you. Okay, because each one tells you, how the code slices are done for each individual instruction. So they can be useful because then you don't have to reinvent the wheel on the fly during the exam. So if you look at inc.c itself, this is the first slice. Now, but you have to know which bit is corresponding, or which bit field is corresponding to what. So you still have to remember how to read these particular numbers. But this tells you, how increment itself is implemented as microcode, which is going to be useful. Okay. So if you don't want to, waste space, you can just, copy this part, to a notepad or some document. Just say that this is increment, okay? And then that's going to be useful when you're working on, that might be helpful in your exam. Just might. Yeah.
I'll say that's the third or fourth time you said that.
Okay.
Then-
That might be helpful. Fourth time. We'll make it a loop, right? Every 5 minutes we'll repeat that. Okay. So there's increment. In this particular case, we have load. And we also have JMP, not JMPI, but just JMP itself. Okay, so there you have it. Now, but those things, those slices by themselves, is useful, but it is also more useful if you know what these things are really connecting to in the processor architecture. Okay, which MUX or demugs are they operating? Are they selecting which operation in the ALU? Are they enabling the flags register? Are they enabling the program counter? So you have to kind of associate these particular values to the constructs of the processor architecture. Which also means, a printout of the processor architecture is going to be, yes. All right, so that one is done. Let's take a look at this one. Okay, some purists feel that the L flag is dirty because it is risky, because it's not risky enough, because it's actually a combination of using the sign flag and the overflow flag. Assume the original code is like this. Okay, in other words, this is now replaced with a JLI to L1. Okay, rewrite this code so that it only relies on LDI, JMP, JC, JC, JO, and a JS. So in our current instruction set, you will basically add an I to all of those instructions, so that you don't have to keep using LDI, 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 LDI. You can just use JMPI, JCI, JCI, and so on and so forth. So the question is, how would you do that? Okay, first of all, what do you remember? What is the L flag? Yep, exclusive OR with the O flag. Okay, so once you know that, so how do you use the JSI, JOI to implement JLI? That's the question. Okay, I'm not giving you this instruction. Can you do the same thing using just JSI, JOI, and JMPI instructions? The answer is yes. It's going to look kind of ugly because you will kind of have all kinds of jumping around and stuff like that. But the answer is yes, you can do it, and you have to kind of figure out how to do it. Okay, so that's one type of question that you might encounter in the final exam. Question number 5, assume the following memory allocation. X_LO is the label of the least significant byte of a signed 16-bit number, and X_high is the label of the most significant byte of the same signed 16-bit number. In the following area, write the assembly code to compute the arithmetic negation of the value x and store it back into the same 2 bytes. So these 2 bytes combined is x, which is a 16-bit signed number. I want to be able to do the arithmetic negation and store it back into these 2 locations. So the question is, how do you do it? So we start off with 2's complement, because that's how we do negation. 2's complement is the same thing as 1's complement plus 1, which is a bitwise knot represented by 2D here, x plus 1. So to do this, these are the instructions that you have to kind of go through to get it done. So the answer is already here, for this particular question. That's actually the answer.
Can we do that one?
Do this one?
Yeah.
That means it's not going to be a part of the questions, right? Yeah, we can do it. You're just making my job harder because otherwise I can just change the question from JL to JLI and I'm done. Just add an I to all the instructions. But now I have to come up with new instructions.
Nah, that's all right. We'll figure it out.
Okay, so JLI L1. How do we implement JLI L1? But only using the other jump instructions. Okay, so that's the question. So the first thing you want to know is JZ may not be very useful. Okay, JC definitely is not going to be helpful. JCI shouldn't be using it. Because JC or the carry flag is only useful after a unsigned comparison. And JL is obviously a signed comparison. So you should be using JSI, JOI, and just JMP itself. Now when you approach a problem like this, I would do it like this, okay? There's no particular order. You just say JSI to some temporary label. I'm just going to call all the temporary label x1, x2, and so on. Okay. So as the usual thing that I do, I'm going to comment what does it mean if I get here. Okay. If I continue execution without branching to x1, that means the sign flag is a 0. So I make a little note here to remind myself what it means. And if I do branch to x1, that means the sign flag is a 1. Okay. Knowing that the sign flag is a 0, what can I do at this point? I can do a JO, right? So if I do a JO at this point, JOI, joy, where should I go? I already know that the sign flag is a 0. JOI will only go to the destination that I specify if the overflow flag is a 1. Wait, if the sign flag is a 0 and the overflow flag is a 1, what does it mean about the L flag? I was 1, and in the original instruction, I should go to L1 when the L flag has a 1, right? So that means this would be a good time to go to L1. Cool. But now you have to ask the question, what if I end up here? What if the branch did not happen? That means sign is 0, and overflow is a 0 as well. So what would the original instruction do when the L flag is a 0? Just continues, right? Just kind of falls through. So now I need to have a unconditional branch of continuation. So we just call this x2, and x2 is really just here as a continuation point. Is that okay? Okay. Now, what should I do over here? I already know that the sign flag is a 1, but the only other instruction I can use is JOI. So let's do a JOI here. The question is, where am I supposed to go with a JOI? Sign is 1 already. JOI means it will branch when the overflow is also a 1. Yep, we should go to x2 because together, when both of these flags are 1s, the L flag is a 0, which means I should continue execution. Which also means at this point, I have just confirmed that the overflow flag is a 0. So where should I go at this point? JMPI, the L1, that's it. So it's a little bit messy, but for people who are kind of purists, and say that we want pure RISC architecture, this is the way you do JLI, which is a lot of stuff. Yep.
I had a question about, kind of assembly code. So I was looking at, other assembly code. They were using like percentage signs to denote registers. So
Yes.
Is that literally the only difference?
That's the AT&T notation. You will see different kind of flavors or dialects when it comes to assembly programming languages. So some programming languages would use special symbols for registers, others do not. Some would use the parentheses to mean dereferencing, and others do not. They would use an @ symbol instead. So they have just variations of the syntax. I just pick whatever is easy to parse using a spreadsheet. Actually, it's the other way around. I make the language first, and then I have to find out how to do it in the spreadsheet. Okay. Any questions? No questions? All right. So this one is a lot more messy because we did not have the I versions of all the instructions. So that's why a lot of LDI stuff here. But we now that we have those instructions, it's a lot easier. Okay. But what I really want to kind of talk about today is continue to talk about subroutine calls with parameters and stuff like that. Except this time, we're going to use the result of a subroutine call as a parameter to another subroutine call. Okay, so we want to figure out how to do that. So I'm going to give you the C code first, just so that we know what kind of C code we're trying to imitate in assembly code. Okay, so let me get this out of the way and write it here. Okay, so we will go ahead and, okay, we can do the same thing, 5, just returns a value of 5. And then we have 7. Returning a value of 7. This time, I'm not going to make it any more complicated than before, because before 7 returns 5 plus 1 plus 1. Okay, so I decided not to make it any more complicated because that's not the focus of what we want to do today. So what we want to do today is to implement the sum function, which takes 2 parameters. It's adding x and y together. So it's just adding x and y. Do we have any questions at this point about these 3 functions, 5, 7, and sum? No
Is it sum a lot
questions?
like add?
Hmm?
Is it sum a lot?
Yeah, it's just basically add.
Okay.
But it's how we call that, or what kind of parameter we use that makes it kind of interesting. Okay. So now we have main. Okay, because I want to make the C program first. So in the main program, I have my local variable x, and x is the summation of 5 and 7. So it is different from your homework assignment because your homework assignment does not have an invocation of a function to supply a value directly as a parameter. This one does. Okay? So it's a little bit different compared to your homework assignment. And main just returns a 0 at this point. So this is what I want to implement in assembly code. Are we doing okay so far with this? Okay. I'm going to put this on the one side so that we can refer to the assembly code. And we'll use a new window on this side to actually implement this is the C code, this is going to be the assembly code. So the assembly code start with the usual stuff. Okay, we're just going to be making sure that the stack pointer starts from location 0, and main officially starts here. Decrement D to allocate for local variable x, and then it's time to perform the calculations. So what am I going to do here? What do I have to do? What is the sequence of operations?
7 first.
7 first because the last parameter is pushed first. Okay? And then 5,
And then sum.
and then sum. Okay? But that's the order of calling the subroutines, but in the process of doing that, we also have to work with the stack carefully as we build up the parameters for sum. Okay? Very good. Okay. So the first thing we need to do, okay, I'm going to just comment here, call 7 first. Okay? So to call 7, we should know the sequence of operations here. The first thing we need to do is to save the return address. So we're going to have main underscore ret1 as the first point of continuation in main. So to do this part, we can use register A at this point. Register A has no particular meaning at this point. So we'll just load immediate A with main ret1. And then we need to allocate 1 byte on the stack as the return address. And then we have to store register A to this location. So that would push the return address main underscore ret1 on the stack. So now that the subroutine knows where to continue execution, we can just go ahead and do a branch jump immediate to the subroutine that we want to call, which is 7. Okay, that should be pretty familiar at this point, with this kind of code. Okay, so this really helps, if you can kind of recognize, okay, we're doing something with a stack, we are doing a store, which means we are putting something on the stack, and we're dealing with a continuation point. Those are all indications that we are calling a subroutine. Okay, so it's really that's going to be helpful when you're asked to decompile a program. You look at the assembly code, and then you try to figure out what it is really doing. So understanding these macros, these chunks of code that has a particular pattern, is going to be helpful. Okay, so that's the first one. What should I do when 7 returns? Are there any parameters to deallocate? 7 does not use any parameters, right? So there's nothing to deallocate at this point. But I do have one thing to do with the stack. What should I do at this point?
You want to push the return value that's stored in A you got from 7 onto the stack so we can use it later after we come back from 5.
That is correct. Well, I'm pushing it on the stack because I'm setting it up as the second parameter to sum.
Right.
Yep. Okay, that's good. Okay, so we do need to push A. So push A, which is the return value of 7 on stack. I'm not going to say push A on stack because push implies that you are storing it on the stack already. All right, so to do this, we first decrement D, okay, allocate for A, or the A that we're going to push, stda, we're going to store register A to the byte pointed to by the stack pointer, and that's it. We have just stored A on the stack. Very good. So now we are ready to call the second function. So that's going to be about the same usual stuff, okay? Except you have to remember to use the next continuation point, which is main underscore return 2, decrement D. And these two instructions, the ordering of these two really does not matter because they don't interfere with each other. They do not have any dependency. So the order can be changed. The next one cannot. Okay, this one has to be done after both of those other instructions are done. So 18 can only be done after line 16 and line 17, but you can reverse the order of line 16 and 17. JMPI to 5 this time, and then main underscore return 2 as the second continuation point. Okay, so once again, what do we need to do here? Yeah, because you have to push A again, because this is our first parameter to sum, we have to push it on the stack again. So that means we just do a decrement D again, stda. Okay, so I'm just going to use a simplified comment here. We're just pushing A again on the stack. So at this point, we have both parameters on the stack for sum. So it's now time to call sum, which is going to be our third continuation point. So LDIA main underscore return 3, decrement D, stda, JMPI to sum, main underscore return 3. Are we doing okay so far with this program? Now this time I do have something to clean up on the stack, don't we? How many things should I clean up before proceeding to do something else? 2 bytes, because the sum subroutine takes 2 parameters and each one is 1 byte. So we have to deallocate those 2 bytes, which is basically just incrementing D by 2, or just doing it twice. So we have to deallocate parameters for sum. What should D be pointing to now at this point?
Local variable again.
Local variable x. Very good. Good job. So D is the same thing as ampersand x. It is the address of x. So I have to store whatever is in A to that. So what do we do? That would do it. Because we are storing, okay, store return value of sum to x. Now, since this program doesn't really do anything with x after this point, I'm not going to do much after this. Okay. So technically speaking, before the halt instruction, you should increment D again, to deallocate local variable x. Even though it doesn't really do anything useful, technically speaking, this is how you balance the stack when you are done with the subroutine. Is that okay? So now we can write the other. Do you guys want to go through how to write the other 3 subroutines, or is this okay? It's a repetition of something that we have done already, so I don't think we need to spend too much time to do that. So is that okay?
Actually, we don't do all of them. We go over the point arithmetic. We need to get at the parameters for sum.
Oh, okay, sure, yeah, exactly. So just sum, right?
Yeah.
Okay. So if you implement sum, the first thing I usually do with a map first is to look at what is on the stack. Okay, so if I look at this, y has the highest address, x has the second one, and then return address will be pointed to by d at the entry point of the subroutine. Okay. Okay. So sum only has one thing to do. It just wants to compute the value of x plus y. So we just need to do a CPR, okay, copy the stack pointer to something else. I almost made that mistake again. Almost, close, not quite. So I'm going to copy that to B. So I'm going to copy D to B. So B is D, okay. And then we want to increment B to by 1, increment B. Okay, so I can also comment here and say that B points to return address at this point. But once I increment B, then B will be pointing to X, which means B is the address of X. It's not X, it is the address of X. So if you want to get the value of X, you have to do an LD instruction. So we can put it into C, okay, because we have that spare register to use. So C is actually the value of parameter X. Is that okay so far? Because we have to track which register has the address and which register has the value of a parameter. Is that okay? Okay. And since I have enough registers, I can just keep incrementing B so that now B is the address of Y. We can do this because I can use A now. So I load, so A is now the value of Y, but I'm supposed to return X plus Y, but X is already in register C, so we can just do an add instruction. The destination is the first operand, which is A. So we're going to add C to A. So now A is X plus Y. And we have the return value in the right register already, so it's time to return at this point to make use of the return address. Should I do something about the stack pointer? Did I do anything with the stack? I did not. All the arithmetics were done with register B, which is not the stack pointer. So I don't have to adjust the stack pointer at all. The stack pointer is still pointing to the return address at this point, because I never really did any increment or decrement with register D. I only did all that stuff with register B, which was a copy of register D. Is that okay? So that means I can just use the usual return code here. LD, other than A, I can use any other register. So B is the return address at this point. Then I can do an increment D to deallocate our return address, and then a JMPB to continue execution in caller. Is that okay? All right. Any questions about this particular sample program? Nope. Okay. What about swap? Okay, have I done the swap subroutine in this class? I don't remember doing that. Okay, so let's go ahead and do swap. Okay. So if I have two integers, one is pointed to by P1 and the other one is pointed to by P2 as parameters, how do I exchange the values pointed to by these two pointers? Okay, so this is the part where I want to kind of make sure that we have a little warm up on pointer related operations, especially as parameters. So I will give you a few incorrect implementations first and see if you can recognize what that would do or what kind of problem you can run into if I do that. Okay, so I'm going to use t here, and I will say t equals to p1, p1 equals to p2, okay, fix the syntax a little bit, and p2 equals to t. What is that going to do? It's not right, okay, but how is it not right? We have a type issue, right? Because t is an int, p1 is the address of an int, and they are not interchangeable. So that means the compiler would actually complain about this one. There's no way I can actually run this code and have it run incorrectly, because the compiler would catch this and go like, can't do this. Okay? So if a CISP 360 student taking, just getting into pointers the first time, what do you think that student may do to try to fix the syntax or the compiler errors? It's not exactly a syntax error, it's a type checking error. What is the worst way to fix this problem?
Declare t as pointers.
No, it can be worse. This is worse.
Better.
Oh, the compiler will be happy about this, right? Because every time, just remember, every time you use typecasting in C and C++, you are basically telling the compiler, I know what I'm doing, don't nag me. Okay? So even if you're about to do something that is not going to work, the compiler will look at typecasting and go like, okay, you think you know what you're doing, I'm not going to do anything, I'm not going to warn you anymore. Okay? But this is bad, okay? Because you're just casting the thing so that the type matches, but you're not doing what it is supposed to do. Because P1 is pointing to the thing that you want to exchange. You're not exchanging P1 itself. Okay? So just as bad, okay, without using typecasting, is this. Well, is this going to crash? Okay, first question is this going to crash the program? Is it going to access a location? Assuming P1 and P2 are passed correctly, okay, the caller did the right thing. Okay, so assuming the caller is giving you correct pointers, okay, is this code going to crash by itself? Is it going to crash? No, it's not going to crash. What is it going to do? As far as the caller is concerned, what is this code going to do? Absolutely nothing. Because it will finish swapping the parameters on the stack. But what is the caller going to do to those parameters as soon as the subroutine returns? Pop it, right? It will just be deallocated. So all this hard work is not going to be of any use whatsoever. Is that okay? So the correct fix to this program is not to make t a pointer, but change p1. Every time you use the pointers, you have to dereference, because you are swapping what the pointers are pointing to and not the pointers themselves. Are we doing okay so far with this code here? This is not assembly related in a way, but because we're trying to implement all of these using our instruction set, we have to be crystal clear in terms of what the code is supposed to do. Okay, all right, so now that we have the right code in C, let's see what we can do in assembly to get this done. Okay, so we have swap as a subroutine, and as usual, I'm going to specify what is on the stack. P2 is on the stack, P1 is on the stack, the return address is on the stack, and initially this is what the stack pointer is pointing to. Okay, so the first thing we need to do is to have our local variable t allocated so that we have a place to store whatever P1 was pointing to, or the value that P1 is pointing to. So that means we have a local variable. So what do we do with a stack pointer to say that, hey, we need a local variable here? Just decrement, okay? Without actually storing anything. Now you can potentially combine the allocation with storing whatever P1 is pointing to. You can do that. It's okay. Do you want me to use the code like that, or do you want to separate the allocation from initializing it? Separate? Okay. All right. Fine. That's good. So we decrement D first to allocate for local variable T. Okay, so now we need to, with an assignment statement, the first thing we need to do is the right-hand side. So we have to dereference P1 first. So this is going to be a lot of dereferencing. CPR A, comma D. Okay, so A equals D. A basically points to the return address. So the next thing we need to do is to increment A. Huh? Oh, A points to T. Yep, correct. Thank you. Good job. Good catch. A points to T. We increment it once. A points to the return address now, which is not what we want. Increment A one more time. Now A points to P1. Does that make any sense? Okay, should we dereference A at this point? Now this is going to be a little bit messy, because what this means is A is the address of P1. P1 itself is a pointer, but at this point I don't even need to know whether P1 is a pointer or not, because the first thing we need is to get to P1 itself. Okay, so we need one dereference. Okay, I'm going to use another register for dereferencing because later on we need to get to P2. We'll see whether we can keep using A or not. Okay, so we'll do a dereference. Every time we say dereference and it's a read operation, it means LD. So we use the load instruction and we'll use register B, for instance, in this case. Okay. So A is now P1, but it is not P1 that I want. On line 47, it's what it points to that I want, right? So I need to dereference it one more time. So now A is whatever P1 points to. Oops, B.
Is it B?
Yep. There we go. There we go. Okay. So B is P1 because we are dereferencing A, which is the address of P1. Once that B is P1, we dereference it one more time so that B is now whatever P1 points to. Okay, very good. All right. Okay. Now that we know what we are supposed to store into T, we have to kind of compute the address of T. Well, we got A pretty close already, right? Because A is pointing to P1 at this point, because I never really dereference or overwrite A after this point. So what I need to do is to have A to go back to here and then go back to here. So we can decrement it twice, okay? Or we can do CPR one more time.
Is it D still pointing to T? D is
Yep,
still pointing to
D
T?
is still pointing to T, so we can do that too. Oh, you're right. Okay, that's easier. So we can do a ST, D, A, B. Okay. Because D is still pointing to the return T at this point. So at this point we are storing, so T is actually getting whatever P1 points to. Is that okay? So I'm just going to make a point here. D is still pointing to T because we made a copy to manipulate A. Is that okay? All right. So we are done with the first line. So one single line in C translates to this kind of lines in assembly. You at least using the toy architecture. Okay. So the next thing we need is to dereference P2 and then store that to whatever P1 points to. So since A is not changed, we can increment A one more time. So now A points to P2, or you can say A is the address of P2. Yeah, it doesn't look like we can reuse let's not reuse the registers from before other than A. So now we do a LDB A. So B is P2 at this point. And then we do a B indirect B. So B is now whatever P2 points to. Are we still doing the same? Are we still doing okay? It's basically the same stuff as before. Okay. So now B is the right-hand side of the second assignment statement. We need to basically figure out where we're going to store that. And there are a few ways to do it. We can decrement A. So A points now to P1. And we need a different register because B is now useful because B has the right-hand side. So we need to use register C for this purpose. So we need to do a LDCA. So C is now P1. Are we still doing okay so far? Okay. And since C is P1, but we don't want to store to C, okay? We don't want to do something like this, okay? This is not what we want to do because this will basically just overwrite the parameter itself on the stack and not what P1 points to. So this is not what we want to do. So we need to do one more thing. C is P1. Oh, it is already there. Okay, so we do want to store it into C. So dereferencing P1 is getting B, but B is whatever P2 points to. So that it does accomplish that. Are we doing okay or not? Can we track all the registers? So far so good or not so?
Messy, but it's clear, but it's messy.
It is messy, correct. Okay, it is messy. Okay, A points to P1, and this is dereferencing. Okay, so we'll use the standard notation. So A is the address of P1. By dereferencing it, C is now P1 itself, and when we dereference C as the destination to store something, then we are basically just dereferencing P1, and since B from earlier has whatever P2 points to, so we got this instruction. We got this line of C code done. Is that okay? So down to the last one. So when we're down to the last one, the first thing we need to do is to retrieve the value of T. Did we do anything with D after the last time we changed it on line 60? Nope. So that means D is still pointing to T, so that's good. All right, so we don't need the other registers anymore. Well, we can kind of keep using A, because it's just another increment of A would get us back to the address of P2, so we can keep using that. So we don't want to mess around with A, we can use B. Okay, so we can use B in this case. And so B is the value of T. Is that okay? Because the stack pointer D is pointing to T at this point. So now we have the right-hand side, we just have to figure out the left-hand side so that we can store the reference to the left-hand side. What is A pointing to at this point? A is pointing to P1, which is not what I want because P1 is over here. So how do I get the stack pointer, not stack pointer, but how do I get A to point to P2, excuse me, point to P2 instead of P1? Increment. Yep, increment D. So, not D, increment A. So the A is now once again the address of P2. But that's not what I want to use, so we need to do a dereference. So we need to do a dereference into, well, after this point I don't need A anymore, so we can just go ahead and dereference it like that. So A is now P2 itself. And then we need a load store instruction, indirect into A. whatever is in B, because B is T. So now we have dereferencing P2 as the left-hand side of the assignment, and the right-hand side is already in B, which is the value of T. That should conclude the swap operation. So we will use the usual return call, which is the return code, which is LD, some register. Now in this particular case, register A has no specific value, no specific meaning, because in C code it is returning a void. In other words, we are not assuming a meaningful return value, so register A is now free to be used in the sequence of returning from the subroutine. Is that part okay? Does everybody understand why I can mess around with A now? Okay. So I can do this. A is my return address at this point. Oh, yep, we have to deallocate. Deallocate T, which is my local variable, so that D is once again pointing to the return address. We load it, and then we increment it one more time. Deallocate the return address, and now we can do the jump using A as the destination. I'm guessing this code works, but guessing is not what we want to do we? So we are gonna test it. So to test this code, I'm gonna, can I remove the first part? I can just use a new document, because I don't want to lose the other one. Okay, so we'll go ahead and copy the swap subroutine. And just add a main to it. Initialize the stack pointer, and this time I have, so here's the halt instruction. After the halt instruction, I'm just going to be lazy. Well, should I be lazy or not? Okay, let me not be lazy, because I don't like the idea of being lazy. So we'll do it the hard way. So in main itself, we'll have two local variables, x and y. X has a value, starts with a value of, I don't know, 56, and y starts with a value of, let's say, -5. And then we'll call the swap subroutine with the address of x and the address of y as parameters, and that's my main. Okay. So when you implement this main in assembly, then if you do it the same in the same sequence as in the C code, then you kind of have to do it the hard way, which is decrementing D to allocate for one of the two variables. Which one is x and which one is y is kind of up to you. Okay, you should not make an assumption of how the compiler allocates for local variables. With parameters, yes, but not with local variables. So in this case, I'm going to allocate for local variable x first, and then we'll allocate for local variable y. Which means on the stack, I'm going to have local variable x and a local variable y after that. Okay. All right. So now we need to store a 56 into x and to store a -5 into y. How do we store 56 into x?
Storage register, storage. No, wait.
Well, you have to compute the address first. Okay, so technically speaking, you have to kind of do the same thing because D is pointing to y at this point, so we have to kind of do some calculations using another register. So A is D, which also means A is the address of y. Increment A, so that A is now the address of x. Okay. And then we do LDI. This one is unavoidable unless you want to use 56 increment instructions. That's the other way to do it without using a constant, but that's much longer than what I'm going to do here. So we'll put 56 into B, and then it becomes a store instruction, indirect A, B. So this is implementing x star A equals to 56, which is basically saying the same thing as x equals to 56. Do we have any questions at this point? Is that okay? All right. Okay. Moving on. The next one, since we have a being x, we just have to increment a one more time. So the a is now the address of y, and we have to do LDIB with -5. And the assembler can only deal with unsigned integers. What does -5 look like as a decimal number representing the unsigned representation of the bit pattern that is also representing -5? Yes?
Wouldn't you have to decrement A instead of increment it, since you stored X first?
Oh, right. Okay. Good point. Because X is here, Y is one byte below that, so it's decremented. Thank you. Okay, so what do we put into B as a base 10 unsigned number, but it would also be representing -5 in a signed representation? Okay, clue, 255, 255 is -1.
Reverse circle.
Keep going, right? I mean, okay, so it's going to be what? 251. Yeah, 251 is -1. Okay. Is -1 in 8-bit representation. Okay. So now we got A, which is the address, B, which is the value. It is time to do a store. So STA B, just like before. So star A equals to -5. Oops. Which also means Y is now -5. Okay, we are now down to line 47. What do we need to do first? We actually got it right there already, don't we? One of the registers already has the address of Y. And that turns out to be the first thing I need to push on the stack as the second parameter. Yep, register A. We got it already. So we can now do a decrement D, right? Allocate for param P2. And then we can now store into that location. Remember, you have to allocate first and then store to that location. So we do a store D, A. Okay. P2, or parameter P2, is now the address of Y. Since Y is one byte below X, and now we need to push X, we just increment A. So that A is now the address of X. Decrement D one more time to allocate for parameter P1, STDA. So the P1 as a parameter is the address of X. Is that okay so far? Okay. Now we can call the subroutine. So we have to designate the return address, okay, where we're going to continue execution in main, and we just have a halt instruction after that. We can probably do another increment D here to deallocate for the two local variables. But before that, we also have to increment D for the parameters. So there are 4 increment Ds here, and I'm going to specify which one is deallocating what. What is this one deallocating? Remember, the deallocation is in opposite order of the allocation. Which parameter? Which is P1, okay? So we deallocate P1, deallocate P2. What about these two? What else is on the stack? So if you look it up here, Y is next, and then we have X. Very good, okay? All right, but we cannot just do this, there's no call here. So we need to do a LDI, a main return, decrement D, This time we are allocating for the return address. stda save return address on the stack, and then a jmpi instruction to continue execution at the subroutine which we call swap. All right. Any questions? You want to run it? Well, we'll see. We'll see. Okay, Control A, Control C. Where's my assembler? There we go. We won't have time to talk about structures. Okay, so no errors. Cool. Okay. All right, so no errors, and then we can go to RAM file and download as CSV. We'll call this swap.csv. And then we go back to the simulator, which I haven't started yet today. And processor W2. There we go. Okay, how do we debug this program? I'm not 100% sure this is going to work. What are the few registers that we really should track in every single program? Okay, D is the stack pointer. It has significance. So we want to, I personally will start with PC, the program counter itself. And then I go to here and track register D. What else should I track in this particular program? Which portion of RAM should I track? So location 255 is going to be local variable X. Location 254 is going to be variable Y. Location 253 is, no, it's not T yet. It is P2. It is parameter 2 to the swap subroutine. One byte below that is 252. That's going to be P1, which is parameter 1 of the swap subroutine. Location 251, the return address, and then 250 is T. Okay, very good. Okay, so we'll track all of those locations. So the key of debugging a program, as you already find out from doing your homework assignment, is to know what is expected in those locations first. So when your program doesn't behave and it gives you something other than what you are expecting, you can then go back and go like, okay, what can cause that to happen, right? So we have X, Y, P2, P1, return address, and T. Is that okay? So I think we got all the really important stuff to track in the log. So we'll go ahead and, I'm just thinking about should I do it in a file. Okay, let's do it in a file. I'm putting it into a file, this is swap.log in the temp folder. And include header line, good, okay, close. All right, shall we let it go? Yep, maximum clock speed. And it has stopped. Okay, I think execution has stopped because the program counter is at 1C, so we can stop the ticking. All right, so what do we do? What do we check first? Is 1C corresponding to the halt instruction or the 1 byte after the halt instruction? That's the first question. So let's go to the assembler and find out. In the assemble tab, we look at the hold instruction. Hold instruction is down here a little bit, right there. And it is, in fact, at location 1B.
It sort of kind of increments up on the whole, right?
Yeah, it goes one more after it, doesn't
Because when you grab the opcode, the whole.
You grab the opcode, but okay, let's see, where? Oh, 1C, that is correct. So 1C is 1 byte after 1B, which is the location of the hold instruction. So the program didn't crash. We're at a point where the PC is supposed to be. So now we can look into the trace and find out whether the memory locations and the registers and stuff like that reflects what they're supposed to be. So we'll use another mouse pad to look at that. So this is swap.log. Okay. It's not wide enough. Yeah, we can decrease the font size. Not quite. We can also change it so that it doesn't wrap around. So we'll see whether it can stop that. Line numbers. There we go. They do line up, I think. Not exactly. Close enough. Yeah, we can figure it out. Okay. So how do you test this program whether it's working or not? I mean, if you're really lazy and you're just looking at the final result compared to what it is supposed to be, how do you check this program? What locations are you going to look into? The local. Yep, exactly, because those are the local variables x and y in main, and the content is supposed to be exchanged. So we want to look at location 255, which is here. Okay, the labels are not exactly right. Okay, they're actually off a little bit. So we have PC and register D. Okay, this is register D. This is location 255. This is location 254. So location 255 starts off with the binary bit pattern of 00111000, which is in hexadecimal. It is a 3-8, which is 3 times 18, which is 48, plus 8, which is 56. So it is 56 here in decimal. This is supposed to be 251 or 251, which is 4 from 255. 255 are all ones, and this one is only missing one of those, and that turns out to be the positions for 4. So we know this bit pattern is also representing 251, which turns out to be the same representation for -5 in 8 bits. -5 in 8 bits. So we got these two locations initialized correctly. That's cool. So we can kind of skip all the stuff in between and see whether the end result is exactly exchanged. And they are exactly exchanged. You can see how 56 is now in location in local variable y, and also 251 or -5 is now in location 255. So the program did what it is supposed to. It did not crash. It got to the halt instruction that it is supposed to get back to. What about the stack pointer? Did the stack pointer get balanced? It started off with a value of 0. It ended with a value of 0 as well. So the stack was balanced. So all the indicators is telling me that this program does work correctly. What about the other two locations? What about these two things? One is, this is location 253. This is location 252. What are those locations for?
The addresses of X and Y.
The address of X is in here. The address of Y is in here. Is that the case? This is the address of X. This is the address of Y. What about T? What is T supposed to have? Because we can see it. I don't want to scroll just yet. I just want to kind of, if we execute the algorithm mentally, what would be in T as my local variable? So let's switch to the mouse pad code first in C. There we go. There we go. So this is the program that we're dealing with. What do you think should be in local variable t? It is supposed to be whatever p1 points to initially, and p1 is the address of x, which means that should be 56. Right? So local variable t of swap is supposed to have the content of local variable x of main, which means it should have a value of 56. So we go back into here, and then we scroll a little bit, and turns out it does have, oops, that's not it, that's the return address. This one here, so it does turn out to have the value of 56. So everything checks out, in this case. But you guys helped caught a lot of the bugs. But that's good. That means you have been doing your homework assignment and you're actually understanding how all this stuff works. Any questions about what we have just talked about? Your homework is studying for the exam. Now, since we have a few minutes left, let's go back to the practice test or the test from the previous semester. And the only one that I really want to go through is the decompiling program. The one where you're given the assembly code and you have to reverse it back to the whatever you can find out about the C code. So do it as much as you can. I'm just trying to find out which tab has it. Got it. Or maybe this one. Yep. This is the one that you can see. So we'll use this one. Okay, so decompiling a program. And let's increase the font size because otherwise it's a little bit harder to read. There we go. All right. So we have main, we have a subroutine. Let's start with the subroutine first. But starting with main is not bad either. Main has x. X is a global variable in this case because x is all the way down here. And x has these 3 bytes, and then we have b is 1. We are subtracting 1, which is b, from d. This is before the decrement instruction was implemented, so we are just decrementing the stack pointer. And then we are storing the return address into b, and then we store b to whatever the stack pointer is pointing to. And this is JMPI to sub1. Before we had JMPI to sub1. So it's longer than your version of the processor because it's lacking some of the really handy instructions that we use in this class. All right. So given this part, what can you tell about the call to sub1? Did we push any parameters on the stack? Nope, there are no parameters on the stack. Okay, so when we get into the subroutine, what is the subroutine doing? Okay, first of all, what is in A? A has the x, has the label x, which means this is going to be the first byte at x. And we are indirectly accessing it. So B is now the first byte at label X. This is just comparing that byte to 0, which is the same thing as AND BB. So it's the same thing as AND BB. We're just checking whether it is 0 or not. This is JZI combined, JZI to else, which means if it is 0, then we continue execution at else, and else is all the way down here. If it is not equal to 0, we will put a 1 into register C. This is incrementing A, and A is some kind of address. We are decrementing decrementing D, which is the stack pointer. We are storing the return address into C, and the return address, okay, this is a continuation point. We're putting into C, and we are storing C onto the stack, and then we are calling. So this is basically recursively calling sub1. Now, how do we, if you just look at the code, what gives away the fact that we are recursively calling sub1?
Calling it inside of itself.
We have a jump to sub1 inside itself, but how do you know it's not a loop? Instead, it is a recursion. What would be the difference between a while loop as opposed to a recursive call?
Return address.
The return address, the use of the stack. Okay, if this is a loop, then it wouldn't be using D at all because D is the stack pointer. But because we are decrementing D, the new instruction set is a whole lot easier to read because we have the decrement instruction instead of this. Okay, so because we're decrementing the stack pointer and we are storing my own return address onto the stack, this is a recursive call. So after the recursive call returns, which means we are continuing execution over here, we are just adding 1 to A, and then we jump all the way to the end. Now the end is just the usual code of returning from a subroutine. Okay. This is else. Else is just putting a 0 into A. So based on what you are seeing here, what do you think this subroutine is doing? It has no parameters because the call did not use any parameters.
Recursively going through an array until it finds a 0 or n.
Yep. And as it returns, what are we doing as it returns? After the recursive call, we are adding 1 to the return value, and then use that as my own return value.
Adding one to.
Yep. This is the recursive version of string length, but without using the stack to pass the parameter. I couldn't do it any more complex code back in those days because the lack of a JMPI instruction and decrement and increment make this code unnecessarily long. But now that we have JMPI, JCI, JZI, this code will be a lot easier to read. So that's the kind of code that you might be asked to analyze to reverse, the assembly code back into C code. Okay. There are a few things that would really stand out. Okay. Every time you see a load instruction or store instruction, it has something to do with dereferencing. Okay, so keep that in mind. But the question is, what are you dereferencing? Are you only dereferencing the address of a parameter, or are you dereferencing a parameter itself? So you kind of have to ask those questions. But these are the only two instructions that can dereference: LD and ST. Anytime you see loading something, storing into the stack, and specify the address a little bit later on, that's a very typical thing that will tell you that this is a call. Okay. The return code typically looks like this. Okay, easier now because now we have a increment instruction. So these two will combine just to increment D in this case. So that's a typical code that that's a return code. Return code. Yep.
Is it return from subroutine or return from anywhere? Or return from
This is how you return at the end of any subroutine.
So it's a return from a subroutine.
Return from a subroutine. Yep. The bottom line is you are continuing execution based on a return address that was stored on stack. All right. Any other questions? No questions? Okay.
So just making sure you wouldn't give us ask us to analyze the older instruction set, you would just have us do the current instructions.
Yes, the current instructions. Well, these are all still current, but it's a lot longer
Because
than
we
it
haven't been
has to be.
focusing on this way.
Right.
You wouldn't ask us
Yeah,
to
so you
do
can
it.
focus on just using increment, decrement, with the JMPI instructions. So I'm not going to intentionally make the code more obscure than it needs to be.
Just making sure.
Yeah, like, adding 56, I'm not gonna do increment, 56 times. It is one way to do it. Well, you don't really have to do increment 56 times, because with a 56, there's an actual trick to do it. Okay, so how do you get to 56 but without using LDI? What is the shortest instruction set to get a particular register with a value of 256? You can use increment, you can use decrement, you can use, you can use increment, you can use decrement, you can use add. Okay, add is bit shifting, very good. Okay, so if you want to look at 56, and you say, okay, how do we express 56? In a very convenient way. 56 is 7 times 8, right? Well, turns out that this is actually very handy, because 7 is a power of 2 minus 1, and 8 is a power of 2. So we can deal with the 8 easy, okay? You just have to add a register to itself 3 times. That's multiplied by 8. That's easy. What about 7? 7 is 8 minus 1, right? Which means, okay, so let's say we want to put 56 into B, okay? So we want to do the equivalent of LDI B 56, but only using increment, decrement, and a single increment, decrement, and a subtract instruction, and add instruction. So this can be done with SUB and B first, okay? So we're just clearing the value of B. Whatever you had before is now 0, okay? And then we say increment 1 or increment B, so the B is now exactly 1. But 1 is not going to do us any good, so we say add BB, add BB, add BB. The first time becomes 2, 4, 8. But that's close, but we don't need exactly 8. So you decrement B by 1. So now it's now 7, right? And then you say add BB, add BB, 14, 28, and 56. Sorry? 9 instructions instead of 56 increments. But this is the kind of trick that you would learn to do, when you're dealing with small, slower architectures, is to look at, this by itself is not that useful, but it tells you something about, how certain values are special. Like multiplied by 10, you can break it down to multiply by 2 plus multiply by 8. Multiply by 2 itself can be done with a shift. Multiply by 8 can also be done with a shift. So when you do multiply by 10, you can break it down into shift operations and addition, instead of looking for the general purpose multiplication subroutine, which is kind of complicated and time consuming. When you guys are growing up with the I family processors and whatnot, you're not gonna have, you won't be doing this until your boss says, okay, we want to make this backpack smart, and do all kinds of tricky things. But we don't want to slap a $20 Raspberry Pi to every product, because we want to be able to sell the backpack for $25 at Walmart, which means you're making the backpack for like 5 cents lower than what you're selling it for. Okay, so your boss is going to say, okay, here's the processor that I want you to use. It's a 25 cents processor. Okay, and it comes with very primitive instructions, and you have to meet the performance requirement, and you have to go through things like this to optimize your code. Okay, you say, oh, we're multiplied by 10. I don't want to go through the general purpose multiplication subroutine, because that's going to be time consuming. So you're going to break it down and go like, oh, okay, shift it by 3 times, store, shift it runs, store, and then add, it's the same thing as multiply by 10. Some of you are laughing right now, just 10 years from now, you're going like, oh, I have the same kind of job that Tech talked about. And you've been liking it too. It's fun. All right, so I'm gonna go to the lab, which is a good time for you guys to ask questions, okay? You can give me some code in C, and ask me how it is going to be implemented. We can do that sort of thing. Just do not ask me what is going to be in the final exam, because I don't know yet.
I just had a quick comment/question. I noticed